lesson that we're going to do for the year of new content. And this isn't really, I mean, it is new content, but it's not any new, it's just kind of using what we already know and applying it in a different way to a point. Okay? Does everybody get my picture though? Ah, thank you. I gotta do something to keep you guys somewhat involved. It is. It is actually. It's out in the parking lot. I didn't see it. All right. So today is 7.2, and right now I have this set to be due Thursday night by midnight, which should be fine. And then Friday we will start 7.3, and so 7.3. I have it set right now for Friday, Monday. We'll see. 7.3 is, I mean, it's not a hard one. So I'm not, my hesitation isn't that it's a hard one. It's just I want to make sure we are thorough on it because it's volume, it's 3D, it's thinking three-dimensionally in your head. And some people it just clicks, and some people it's more thought that goes into it to actually be able to picture what's going on. And so Friday's a good one though. I enjoy going over that lesson, working through those types of problems. And then we'll start to figure out, and again, I'm probably overhyping this, but we'll start to figure out how to do those volumes, and then all of a sudden they'll switch the axis of revolution. And then that changes up our whole thought process. We gotta like reevaluate what the shape is, but we'll get to that. So today, areas in a plane, plane just meaning two-dimensional, XY axis, that's all we're working with, okay? We're gonna look at areas between curves, area enclosed by intersecting curves, boundaries, meaning kind of our limits of integration, but then also integrating with respect to y. And we'll get into what that means. Like all of our integrals, we've always pretty much done dx, something dx, something dx. So we've done some dt stuff in there, okay? But still, when we did dt, like time was on the horizontal axis. Well, now we're going to do dy, and we're going to start to think vertically. We'll get to that, okay? All right, so 7.2, areas in a plane. Well, I got to unfreeze so you can actually see what I see. There we go. Up to this point, we focused on area under a curve. All right, more specifically in relation to the x-axis. If it's above the x-axis, we do our integral. That gives us the area from the x-axis up to the curve. If our curve is below the x-axis, it gives us a negative of the area that's below the x-axis. Now we could have intersecting curves going on, and then we could specify a certain shape. I mean, it'd be kind of an abstract shape though, but some sort of shape that might enclose an area. Okay, so like if we had something, there it is, like that. If we had two curves going on, and I only want the area of that green section, is what we're going to focus on today. Well, how can I find just the area of the green section? Okay, so same shape, it's a little bit bigger. So this blue line is square root of x, and then the bottom line is x squared. So these are inverses of each other, but that's not the purpose of this lesson. If we want to find just this area, okay, very fundamental. If I had some square going on and I had a circle in the middle of it, if I wanted to find just this area, well, I could find the area of the entire square, and I could subtract the area of the circle, and that would leave me with just the area outside of the circle, but still in the square. So same idea now when we're looking with curves. If I were to look at this blue line, and I were to integrate this blue line, that would give me area all the way down to the x-axis. if I were to integrate the red line, I would go from the red line down to the x-axis. So we can start to see, okay, if I take the whole thing with that blue line down and subtract out this white space underneath the red, that's going to leave me with just the green. All right. So it is taking that top line and subtracting the bottom line from it. So I would have square root of x would be my top line, and I'm going to subtract x squared, and all of this is my function dx. You're getting ahead of me. Yep. Yes, we're going to do that. Okay. But this cuts off. We only want the area from here to the left. Okay. If we did an indefinite integral right now, which what we have, this is going to continue on and on and on. Well, we have to create those bounds, those boundaries. And so this would go from 0 to 1 as a definite integral. Okay, because 0 to 1 of my blue line, my root x, that's going to give me all of this area. 0 to 1 of x squared is going to give me essentially this white space. So I'm going to take the whole thing, subtract out the white space, and that's only going to leave me with the green. Okay, and this is unofficial, but how I always think about it, I create my integral from some a to b, which is just those boundaries, and I literally think top line minus bottom line. That's what my integral will be every single time. But you have to take that with a grain of salt and think, okay, if these curves were actually below the x-axis, I know my integral is going to go from the curve back up to my x-axis. So always take it in relation to the x-axis. So if it's all below, you're going to go the furthest line below, subtract the line above. Okay, but in general, I always think top line, bottom line, top meaning furthest from the x-axis, bottom meaning closest to the x-axis. So even if it's all below the x-axis, it's really the lowest subtract the highest. Okay. All right, so that's how we find area between two curves. So let's actually do one. So this one, what is the area between negative x squared plus 3 and y equals x? Okay, I mean, the first thing you have to do, which is very fundamental, but you have to know which is which. Okay, I know this is my line. Oops. This is my line y equals x, and this is my line y equals negative x squared plus 3. So whatever functions they give you, you need to know which line represents which function. And it says the area between these two curves. Well, the only area that I will have between these two curves is going to be all of this in here. So it has to be bounded. Right? Just this green shaded area is my only area that's between the curves. I'm not looking down here at all. I'm not looking over here at all. I'm only looking at that area that's bound by each. Okay, so we're going to set up our definite integral. We're going to have the top line. Still from this one, we can treat this as a top line. Okay, I know I said that about going, we're not going to set up two separate integrals and then do this and this, and then this and this. You can still treat it as one. And so this would be a negative x squared plus 3, but then minus x. All right, but we need to know the bounds on this integral. The bounds are going to be these points right here, where my lines intersect, that creates boundary points, that the area is in between those. How can I figure out what these points are? Jacob. You could set these equal to each other. And so if we said, we said negative x squared plus 3 will be equal to x. So where are those two equal to each other at? Okay, well, I could say, well, then I'll bring all this stuff over and set it equal to 0. So now it'd be a positive x squared, still a positive x, but then minus 3. Okay, now I have a quadratic. This is not a nice quadratic that is factorable. What's another way that we could solve the quadratic? What? Quadratic formula. We could do that. Okay. I'm not testing you if you can do the quadratic formula correctly or not. I mean, I expect you to be able to do it. Remember in our calculator, we had that polytools option. Remember that polytools? That you could put a quadratic right into there, hit enter, and it'll spit out what the answer is. Okay, so this one I would probably just use polytools. I'm trying, this is a intermediary step in trying to solve this final answer. They're asking me for the area. I need to know how to solve a quadratic. But again, if you have menu, algebra, I think, polynomial tools, roots of the polynomial, put in 1 for the coefficient on x squared, 1 for the coefficient on x, -3 for your constant. It will tell you that x is -2.3 and x is 1.3. All right, and exactly what that means is right here, it's crossing at -2.3 for an x value and 1.3 for an x value. So those are our bounds. So it's -2.3 all the way up to 1.3. And now we're at a step where you can just put it into our calculator. If this was a no calculator one, it probably wouldn't have gave you decimal bounds for a no calculator one, but the integrand, that -x plus 3 minus x, we could do that integration by hand, okay? Adding and subtracting, you can just take each term. There's no u substitution or anything going on, okay? But for this one, I trust that you can put it right into your calculator and you'll end up with 7.812. That represents the area, this green shaded area, the area between these two curves. So we find our region, we find the bounds of the region. The bounds become our upper and lower limit of integration. Put that all in, gives us the answer. Easy enough, right? Jacob. Anybody else gets 14? Shouldn't be. Double check that. For 3, -2.3, 1.3. Oh, that should be -x squared. That should be -x squared. Yep, my mistake there. -x squared. Okay, so now let's go a little further or more specific We can find area also using subregions. So this one says, find the area of the region that is bound above the x-axis. So we're only looking above the x-axis. And below the line, y equals root x, and the line, y equals x minus 2. Okay, so first off, we have to identify what our lines are. So this one is worded how you will see a math Excel problem worded as well, and I want to be specific on here. Okay, so the area of the region that is bound above the x-axis, okay? So that's easy enough. We know we're going above the x-axis. And below the line square root of x and the line y equals x minus 2. This is not saying below the line y equals x minus 2. It's only talking about below the line y equals root x. And then the other, like the third bound, is the line y equals x minus 2. So we are trying to find this area right here. So it's bound underneath the red line, but it's also bound by that blue line. So that's the area we're trying to find. So again, the area bounded above the x, below the y, and when it says and, meaning the third bound is the line y equals 2. So don't think of that below the line y equals 2, because if you read it wrong or you interpret it wrong, you're thinking this area, but this red line goes off to infinity, this x-axis goes off to infinity, you're not going to be able to find this area. It's not possible because it goes on to infinity. All right, so we want to have a clearly defined region that we're trying to find the area of. So there's at least one question in Math Excel like this, and so treat it as those are all boundary lines. Don't interpret that as below the line y equals root x and below the line y equals x minus 2. Y equals x minus 2 is the third bound. Okay? All right. So it's bounded above the x-axis and below the y and the line y equals x minus 2. So we want to find the area of this region. So we need to figure out boundary points. Well, this one's pretty straightforward. It's right here at 4. This one's nice. This one's right here at 2. So there's no algebra or anything that I had to figure out where these are intersecting at. These ones are pretty nice. And they're not going to give you a graph most often on these questions either. So you're going to have to graph these in your calculator to see what they look like. So I'm putting these up because this is how we solve them, but they'll just give you that statement without any sort of graph. You have to graph it and then determine from there. Okay, so I know I'm going to do an integration. If I were to integrate my line of y equals x, I have something weird going on here. If I go under the line all the way up here to 2, yeah, that gives me the area of this section. But if I go under my line from 2 to 4, that gives me all of this area, but I don't want all of that area. Okay? I mean, you could do it kind of a longer way. That second area is kind of how we've done it in the past, but you're not going to set up, or in the past as in the last 10 minutes, you're not going to do it as square root of x minus this line with bounds from 0 to 4, because it's going to take into account this, and we don't want this. So we are going to do it in subregions. So I'm going to divide this up, and I'm going to call this my region 1 and this my region 2. Find the area of each. add them up, that gives me the area for my shape that I'm working with. So if I want to find the area of region 1, it's going to be my integral from 0 to 2 of just root x dx. Right, because that will be below the red line. And it's always, our integral always takes it with respect to this x-axis, so it's not dipping below the x-axis because I don't want anything down there. All right, this one I'll tell you comes out to be a decimal answer. Well, Math Excel is then going to put the spin on it, give it the exact answer. So let's do this one by hand. So this is really 0 to 2 of x to the 1/2 dx. What's the antiderivative of x raised to the 1/2? So 2/3 x to the 3/2 evaluated from 0 to 2. I don't really have to worry about the 0 because that becomes 0. So it's 2/3 times 2 raised to the 3/2. Okay, and so this is going to become 2/3 to the square root of, would this be 2 cubed? So it'd be 8. What's the square root of 8 in simplest form? 2 root 2. Okay, so times 2 root 2. And so really this now becomes 4 root 2 over 3 would represent the area of region 1. Like I said, I did it out by hand because Math Excel is going to ask for some of these problems exact. So we can't forget how we evaluate by hand, that we can do these integrals by hand. All right, and then now region 2, it's going to be bound from 2 to 4. All right, all I'm worried about now is the second region, which goes from 2 to 4. Now I can treat it as top line minus bottom line. And all of this integrated with respect to x. All right, this one we could integrate by hand. Okay, so this would be 2/3 x raised to the 3/2 minus 1/2 x squared. And then it's a negative of a negative, so this is really plus 2x evaluated from 2 to 4. All right, and this is one we could do with that fundamental theorem of calculus, and I'll just tell you it ends up being 10/3 minus 4 root 2 over 3. All right, so something should pop out at you there. So now if I added together region 1 plus region 2, I have 4 root 2 over 3 plus 10 over 3 minus 4 root 2 over 3. Those are opposites, so I don't have to worry about that. So the area of this region, 10/3. Yes, Lena. Say again. So if you do an integral from 0 to 2 and you include this x minus 2, it's going to find this part as well. And you don't want to find that part. What's that? Okay. From 2 to 4. Yeah, that's what we did. Yep. So what Lena was saying, if you just did the whole thing from 0 to 4 in one integral where you did top minus the bottom, okay, what it's going to do, it's going to include this triangle here, which you don't want. Okay, because it's going to integrate this.
Mr. Army.
Yes.
So y equals the square root of 2 from 0 to 4. That includes the triangle underneath y equals.
What square root of 2? What do you mean? Square root of
I
x?
mean the root x.
Okay, so that's giving you this region 1. It's not counting this.
Oh my gosh. You would do this whole thing and then subtract this. Can you do that?
No, because that's going to count this.
But not this.
It doesn't.
It would just be this whole line.
I know, but if you're saying if you integrate from 0 to 4 of x minus 2.
No, not that. Just
I know.
0 to 4, y equals the square root of x. That just gives you this whole thing. Correct?
Correct.
And then 2 times 2 times 1/2, and then you subtract this area minus that.
Yeah, and that's the same thing essentially was what's happening. Okay? Okay, there's more.
Okay.
I'm going to show you a way here in a second. It's even easier. So, okay? So, subregions, you can isolate subregions, change your bounds, and it will give you only the areas that you want. Add up the areas, and you got it. Jacob.
So why for step 2, if you use the 2 and 4 of x minus x minus?
Because this is like the first example that we did, where we do top line minus bottom line. Because we're only looking at this. Let's look at like this square block.
But can you just have done root x from 0 to 4 minus x minus 2 to 4?
Well, that's what we did. So first off, you found this one, and then you find this one. So sub-regions. So do it 2 separate regions. Okay, you guys are all saying the same thing. It's taking you 3-4 steps to get to the same answer. If your way makes sense and you get the same answer, I don't care. I'm saying this is how you can do it. It's still going to take more than 1 step. Okay, here we go. Integrating with respect to y. So this is gonna alter your thinking a little bit, not much. Okay, but we gotta adjust our thinking a little bit when we're integrating with respect to y. Okay, so sometimes the boundaries of a region are more easily described by functions of y than functions of x. So functions of x would be like f of x equals 2x. That's a function of x. A function of y would be f of y equals 2y. That's what it means, a function of y. Okay. We can still use rectangles to approximate. So when we have a curve and whatever it looks like, remember all we're doing is adding up infinite number of rectangles, but we've always drawn the rectangles vertically, and the width of the rectangle is that dx. All right, so all of our integration, we've always done it with dx, thinking vertical rectangles. Well, now we're going to change it up. We're going to use horizontal rectangles and integrate with respect to y instead. Okay. The resulting basic formula has y in place of x. So now if we're integrating with respect to y, we got to change up our equations a little bit. But this helps to eliminate subregions. Okay, because on that last one, that 0 to 2, below the x-axis, we didn't want that triangle in there. Okay, so that's why we had to do it in 2 separate subregions. Well, now if we change it up and we think horizontally, we can play with it a little bit more. Okay, so if we had a shape like this, we're going to make horizontal rectangles. But look at our functions are now x equals instead of y equals. So we have to create functions as x equals, so as a function of y, so x equals some gy or x equals some fy. So again, we're kind of adjusting our thinking, rotating it to now go left to the y-axis rather than down to the x-axis. We're going left to the y. So now the area of this blue shaded region would be bounds from C to D on the y-axis. So our bounds are changing as well. We're rotating where our bounds are occurring. They're not occurring on the x-axis anymore. They're occurring on the y-axis. But we still think smallest to largest. So C to D will be our bounds. And then it's, in this case, in all cases, furthest from the y-axis subtracts closest to the y-axis. All right, so again, same fundamental concept. When we're on the x, we go furthest from the x to closest to the x. Well, now when we're integrating with respect to y, we're going furthest from the y to closest to the y. Hello. I got about 10, 15 more minutes. All right. Less than that. Okay, so I understand how our thinking is adjusted here. So let's look at the same problem. So this is the exact same one we just did a second ago. We know the answer is 10/3. Okay. So same shape going on. This is our line y equals x minus 2. This is our line y equals square root of x. But now we're going to think of it as horizontal rectangles. And we're adding up horizontal rectangles vertically. Okay, so we need to create our new function. So we're going to have our integral. Our new bounds are going to be from down here at -2 all the way up to here at a +2. Or back that up. We don't want that. We want to go from 0 because we're just trying to find that area above the x-axis. So take that back. It's 0 to 2. We're only working up here. Now there's nothing standing in our way of all of these vertical rectangles. We can go from the x-axis all the way up to the red curve. There's nothing in our way. On the right, it's bound by the blue line. We have to rewrite these equations, though. Instead of y equaling square root of x, we want it to be x equals. Okay? So if I'm looking at my square root of x, I'm going to switch these around. So x would equal square root of y, or back that up. X would then equal y squared. Okay, because if we squared both sides here, we would have it being x equals. And then on this one, I'm going to have y plus 2 now equals x. This is important. We have to get both lines in terms of x equals. So now our integral is going to be y plus 2 for my far right line, subtract y squared dy. So now we don't have to do anything with subregions because there's nothing in our way here. It's basically the right line subtract the left line because it's taking the area going back horizontally towards the y-axis. Work all this out. You could put it in your calculator, but it ends up being 10/3. Same thing. So you'll be given problems that they won't tell you to integrate with respect to y. You have to make that determination and say, oh, I could do this one easier with respect to y than I could with respect to x. The integration of it anyway. There's a little bit of work that you'd have to do to set these equations as x equals. Your bounds are on the y-axis now, but the process works the same after that. Okay. All right, so 7.2 is in Math Excel, due Thursday by midnight. And then Friday we'll start. Tomorrow will be a work day, so we'll start 7.3 on Friday.